You would never have, the point where there's no. All right. So now we're going to look at size. So struct X is like this. Okay, so I have char A, char B, int I. So what you do is fill out the table and then determine what size of struct A will evaluate. What is the size of that struct? Okay, so let's do it. 1, 1, 4. Size equals 8. So you can see here what I've got is A, B, 2 wasted bytes, and then I 4 bytes of I. That's the right bytes. That makes sense? Questions? All right. So what about this one now? Same thing. Fill out the table, determine its size. Okay. Offset to I. 4, right? Because it needs to be a line. Offset to B. 8, because this took 4 things. Size of what?
Nine.
Right here, 9. Who says 9? Any other numbers? 12. Any other numbers? How would I find out? Well, I can go over this program. I can just print it out. So here it is. Over here, there's direct Y. I don't even need any of this, right? Who thinks it's 9? Who thinks it's 12? Wow. Very small number of people think it's 12. Okay. 12. Why?
Keep it aligned.
Why?
Keep it aligned.
Huh?
They want to make sure that when you're writing to the next
But
point
this
in
is
memory.
the end. Why is inputting, answer is 12, right? So what's happening? It is because of alignment. So what's happening here is we have got A, and then we had to waste 3 bytes, and then we have I 4 times, right? And then we have B, and then it wasted 3 more bytes at the end. That seems stupid. What? There's nothing here that has to be aligned. Why? What do you mean a second?
Like, what if we put in the same structure underneath, right? Then what
Say it again.
Like if we put the same structure underneath the second one?
Oh, well,
So like
no, that doesn't matter. No, so actually, that's a really good point. So what if I had some variable, struct A an X, and then struct A Y. The compiler allocates these two things separately. They don't have to be contiguous. It can always add the wasted space here. But also remember that if these are global variables, it can move that up there and use up some of that space. You're so close to the right answer, but there it doesn't matter. But there's another place it does matter. Array, exactly. So what if I did this? I have struct A, little a, so 2. What is that? Well, it's just like it was an array of ints. I have 2 structs. So inside of this struct, I've got, what is it, A, 3 things, got 4 i's, and a B. And if that was it, if this is 9 bytes long, and if this starts off, say at address 1000, arrays, the elements have to be contiguous, remember, because I'm going to use, to access an array, you take the index, so this is a sub 1, index is 1, I take the index times the size and add it to the base address. That's how I get the address of this element. So if this is of size 9, I'm going to take 1 times 9, add it to the base, and this must be at 1009. And what's wrong with that? I is not aligned anymore. So what address will I be at? It's like 1013. It's 1000D if we're doing this in hex. 13 bytes from the beginning, because it's at offset 4 from the beginning of the struct. Well, this struct starts at 1009, so it's 1009, and that's not aligned. So the compiler will add padding to the end of a struct, so that if you have an array of them, everything in the struct that needs to be aligned is still aligned. Okay. So let's introduce the program here. One thing I can do is I can say, so we had offset up, there's also a line. I think it's a line, maybe it's a line. It's a line. It'll either compile or won't compile. I'm letting know my other problems I can't spell. Okay, so what that tells me is that struct, that struct Y, has an alignment requirement of 4. So which means that its size will always be a multiple of 4. Where did the 4 come from? Int. So what it does is it looks at the struct, finds the biggest thing in the struct that's one of these things, and that becomes the alignment. So if this, for example, is a long, now what's the alignment? And let's print the size too. that's a char? Size 1, size 3. What if this is an array of 1,000 chars? Same. Doesn't matter. That array is embedded in this, so that the size is 1,000 or 100. It's 102. But you don't have to align to 100. What if I had this? Four. Yeah, not 8. 4. Change one of these to a long, though. Now what is it? 8. Very good. So play around with that a little bit. I'm blind. Or it has to be. All right, so that's just a few more things to do here. So, we just did the sizes. I've already talked about what it means. So the top thing is an array of struct. It's just like an array of int. That's copies of the struct. The second thing, what's that? Struct S star B bracket. What is that? It's a static array of pointers to structs. It's like this. And that's going to point to a struct we know. What if I had this? Struct as star star. Who likes that? No one. Simple though. This is struct star, what is it? S star B, right? That's a static array of struct. This is a dynamic array of the same thing, so that's this. Same thing with ints, so on. Here, if you have an array, what the offset was in the previous slide. What's the offset to J? Well, that whole entire array, 10 ints is in the struct. So it's 44. Exactly. Whereas in this case, that's just a pointer. Questions? If you have questions, feel free to ask about structs. I just want to say a little bit about dynamic application before we go. This is where we're heading. It's the thing that's really quite different between C and Java. Okay, so we know that allocation, dynamic allocation, includes a call to malloc or new. This starts the lifetime of an object. But there has to also be a corresponding deallocation somewhere. So if you don't eventually deallocate at some point, then what happens is as your program runs, every time it calls malloc, it consumes more memory. And that, the amount of memory used by the program increases monotonically, it never decreases. And this means that that program runs for long enough, it gets too big. And what happens when a program gets too big?
Memory.
Yeah, it overflows something. What does it overflow?
Whatever's next.
It's overflowing how much memory you bought from your computer. It actually will keep running because of something called virtual memory. We have 64 bits of addressing, so it'll just keep growing. Eventually the operating system might kill it. But what happens is you run out of actual memory. So I don't know, how much memory do you have in your laptops? Anybody know? Tablets? How many? 8 gig? 32 gig. You drive a Ferrari? 32 gig. Anybody have board games? Okay, that's gotta be the upper limit. So eventually you run a program, let's say it's the operating system or a web server or maybe a video game, something that runs for a long time that does a lot of dynamic allocation. When it gets up to the size of 32 gigabytes, well, everybody else, the program started to run really, really slow, much earlier. But for you, it kept going for a while. But now, even for you, it won't run. So that is a bug. We call that kind of bug memory leak. So the idea, the name comes from the idea that if you don't deallocate things when you're done, then the amount of memory that's available to your program is leaking away to these things that you allocated and you've never used. Or I mean, you've used, but you don't use them anymore. So here, Java, on one hand, and C and C++ on the other hand, take a completely different perspective. So in Java, how are things deallocated? You know?
Automatic garbage collection.
By the garbage collector. So garbage collector is a background process that uses the following heuristic to determine what it can deallocate. It takes all the pointers in your program. It knows where the pointers are. It follows them and traverses all the links to find all of the objects that your program could possibly access. And those are called reachable objects. Anything else, so this is an object you don't have a pointer to anymore, a reference to anymore in your program, that's garbage. And it claims this. Now, what percentage of Java programs do you think have memory leaks? Right. Yes. Who said all of them? Yeah, you're absolutely right. Pretty much all of them. And it's because this heuristic is too, it's not conservative. So C and C++ take this other perspective, which is that you have to deallocate things manually yourself, which potentially means you can eliminate memory leaks. You can also eliminate them in Java, but it takes some extra work that most people don't do. So that's what we're going to look at next time, and this makes C and C++ programs much more error prone than the way it spends some time. So have a great weekend.